Okay, hello to everyone and welcome. This is the third class in our Schiller Institute class series on Lyndon LaRouche's physical economics. My name is Megan Beets and let's get started. So last week in class 2, we looked at the notion of economic value from the standpoint of physical economy, physical value. So we went through some of LaRouche's ideas and discoveries in terms of how you measure whether or not an action is valuable to an economic system. We looked at the metrics of, for example, potential relative population density, whether or not an activity or a product in the economy contributes to increasing a society's potential relative population density and increasing the rate of increase. That's a true measurement of value. We looked at the effect of technology on the productive powers of the labor force, and we looked at some of how Lyndon LaRouche used thoughts and heuristics from thermodynamics to look at the processes of change over time in the relationships of the labor force and productive activity in the economy. So this week, our theme is Dispensing with the Fraud of Limits to Growth. Now, before we dive in, I want you to think about something. The world's population today is 7.8 billion people. Now, I want you to try to guess in your mind, when it was, what year did the world population reach 1 billion people? 1802, just over 200 years ago, was the first time that the world population was 1 billion. Now I want you to try to guess what the world population was at the time of the 1969 moon landing, which was, 160-something years later. 3.5 billion. So it took all of human history to be able to sustain a population of 1 billion people, and it took less than 200 years to sustain more than triple that. Now, we reached 7 billion people in 2011, and in less than a decade, we're nearing 8 billion. Now, my question, holding all of that in your mind, is how many people should we have on Earth? What's the right number? How many people are too many? Now, last week, I showed a clip of Lyndon LaRouche speaking in 1988, where LaRouche said that if we applied the levels of technology that we already have to the productive process around the world, we would have a potential population density on the planet of 100 billion people living longer, healthier, less crowded lives than we live today. So why is this fight over the idea that there are or are not limits to growth? Why is this so crucial today? And why are we taking this up in an economics class? Well, the reason is not only because the notion that there are limits to growth is untrue, which it is. More than that, it's been the big lie, which has been imposed on nations and perpetuated in order to maintain a colonial system, a colonial arrangement in the world, to keep nations, to keep peoples underdeveloped. And it's done in the name of being natural. Now, I want to give you an example. This was said in 2013 to a large gathering of students in South Africa. Ultimately, if you think about all the youth that everybody has mentioned here in Africa, if everybody is raising living standards to the point where everybody has got a car, and everybody has got air conditioning, and everybody has got a big house, well, the planet will boil over. Now, that was President Barack Obama telling a room full of young people in South Africa that their aspirations to have a standard of living equal with the rest of the world would probably cause the planet to boil over. Now, this is a nation where the official, at least at that time, the official unemployment rate was almost 28%, where 1/5 of people were officially below the poverty line, which is, the extreme poverty line. So this is the fight. And the truth is that unlike animals, human beings are the only species for which there is no limit to progress, for which our growth, our expansion, our progress in and over the universe are potentially infinite. It never has to stop. And I find this to be an incredibly exciting concept and mission in terms of designing an economic system to support that potential. So we're going to get a little bit into that today. Now, so our topic today is resources, or the question or the assertion that there are or are not limits to resources. The first real resource that humanity used was fire, the use of fire. And Lyndon LaRouche often referred to Prometheus, the firebringer, who stole fire from the gods. And who were the gods? It was the oligarchy. It was the oligarchs. It was the emperors, the tyrants of Mount Olympus. And Prometheus gave fire to mankind. And we know from the drama of Aeschylus, from the lips of Prometheus, that fire was not only fire, it was science. It was astronomy, poetry, metallurgy, shipbuilding, agriculture, the things that demonstrate our nature as human. Now, that story is pretty familiar to people today. What's not always remembered is not just that Prometheus stole fire, but why he stole fire, why he took that risk. And the reason is because Zeus, the tyrant, the oligarch, was about to wipe out mankind. Why? Because he was sick of them, because he hated them, and he wanted to replace them with a different species. Now, that is the root of the idea that there are limits to growth. Oligarchy, the attempt to maintain a system where some are born to rule and most are born to serve. Now, I want to look at a more modern manifestation of this Zeusian idea, and that is in the words of somebody who might be familiar to you, at least in name, and that is Thomas Malthus. So let's pull that slide up if we can. Here's Thomas Malthus, and here is what Malthus said, and people may have heard the word Malthusian, which usually comes to mean anti-people. Malthus was anti-people. He wrote, in 1798, he wrote something called an essay on the principle of population. Now, this was not Malthus's original work. He plagiarized it. And he plagiarized it from an Italian named Gianmaria Ortez. And Ortez is known for inventing or coming up with the idea that the planet had a carrying capacity. And Ortez wrote that in response to a pamphlet that was written by Benjamin Franklin called Observations Concerning the Increase of Mankind, where Franklin made an argument for the expansion of the population in North America. Okay, so Malthus took the work of Ortez, plagiarized it on behalf of his employer. Now, who was his employer? The British East India Company. And for this wonderful work, Malthus was rewarded with a professorship at the Haileybury College of the British East India Company, where he was in the fine company of Adam Smith and others, David Ricardo and others. Okay, now what was Malthus's argument in this writing? Well, his argument was that population grows geometrically, but food, agriculture, production of food, only grows arithmetically. Now, you might be wondering, where'd he get that? Nobody knows. But his argument is that if the population increases geometrically, while food increases arithmetically, soon the population will outrun its ability to produce food, and we're all going to starve unless we do nature's job for it and reduce the population on purpose. Now, what Malthus meant by the population was certainly not the fine professors at the Haileybury School. It was the poor. Here's what he said in 1798. Instead of recommending cleanliness to the poor, we should encourage contrary habits. In our towns, we should make the streets narrower, crowd more people into the houses, and court the return of the plague. In the country, we should build our villages near stagnant pools, and particularly encourage settlements in all marshy and unwholesome situations. But above all, we should reprobate specific remedies for ravaging diseases. And those benevolent but much mistaken men who have thought they were doing a service to mankind by projecting schemes for the total extirpation of particular disorders. If by these and similar means the annual mortality were increased, we might probably every one of us marry at the age of puberty, and yet few be absolutely starved. So you see what a fine fellow Thomas Malthus was. Now continuing into the 20th century, into what became the modern environmentalist movement. Environmentalism, as we know it today, was founded at the turn of the 20th century in Britain by the same people who had founded and were running the eugenics societies, race science. These were people such as Julian Huxley, Max Nicholson, who was the Privy Councillor to the Queen, Prince Bernhard of the Netherlands, who was a card-carrying member of the Nazi Party until he was forced to resign and signed his resignation letter, Heil Hitler. So these fine people founded the conservation movement, and this became the face of the eugenics movement after World War II, at the point that eugenics was deemed socially unacceptable. Now, despite that, Huxley in 1946, the year after the world defeated fascism and began to uncover the horrors of the Nazi regime, Julian Huxley delivered a speech at the founding conference of UNESCO, and he said the following. Oh, there's Julian Huxley there, yes. So Huxley said this: "Thus, even though it is quite true that any radical eugenic policy will be for many years politically and psychologically impossible, it will be important for UNESCO to see that the eugenic problem is examined with the greatest care, and that the public mind is informed of the issues at stake, so that much of what now is unthinkable may at least become thinkable." Now, he said in 1948, just 2 years later, he said at the launching of the ecology and conservation movement, he said, "The spread of man must take second place to the conservation of species." Now, to give you a sense of the role that Huxley played, leading up to this period of World War II, in the 1930s, Huxley helped found an organization in Britain called the Political and Economic Planning, or called Political and Economic Planning. This was a board in the British government which promoted the kind of fascist economic policies which were implemented by Mussolini. Huxley worked with the Eugenics Society, of which he was a member and later became the head, to found two organizations in Britain: the Population Policy Committee and the Royal Commission on Population, both of which produced studies on the terrible effects of population growth on resources. Now in 1960, Huxley was in his 60s, and he traveled for many months in Africa. And when he came back, Huxley wrote a number of articles which said that these newly independent African nations could not be trusted with the stewardship of the natural species and resources in their nations. Therefore, he called for an international body which would take up stewardship of these lands. Now, he followed that up by creating such an international body in 1961 called the World Wildlife Fund, which I'm sure many of you have heard of. And he founded it along with Max Nicholson, the Queen's Privy Councillor, and Prince Philip, the royal consort of the Queen, who said many times that he would like to be reborn as a deadly virus to contribute something to solving overpopulation. Now, despite that grand qualification, Prince Philip was not the first head of the WWF, but instead they called upon the talents of Prince Bernhard. So, the WWF and the environmentalist movement were founded by eugenicists and Nazis. Now, to show you that they weren't joking in the creation of the WWF, let me give you a statistic. By the mid-1990s, the WWF had gained control of nearly 2 million square kilometers on the continent of Africa, which is roughly 8% of the entire land area. This land was cordoned off, was turned into wildlife preserves, and the nations of which these lands were a part were denied all access to the development of the resources therein for the benefit of their populations. Now, this hasn't been done only on the continent of Africa. It's been done in Central America, South Asia. For example, between Central America and South America, you have the Darien Gap, which is a region of land that has never been developed. There is no road, rail, no kind of connection where you can drive or travel from Central America into South America because the WWF has cordoned off this entire land area as a nature preserve. Now, in 1968, an organization was founded called the Club of Rome. And the Club of Rome was founded by some of the nastiest, moneyed, and oligarchical interests in Europe. And this is an organization which the LaRouche movement has fought quite energetically throughout our existence, or throughout its existence. We can pull up the slide. In 1972, the Club of Rome released a book called The Limits to Growth. And then you see on the right the book written by Lyndon LaRouche in 1982 called, or I think 1983, called There Are No Limits to Growth. Now, the Limits to Growth study basically was a collection of completely incompetent garbage computer models. We can go to the next slide. I think I have it on the next slide now. Yeah, it's kind of hard to make out what's going on there, but you have these completely garbage computer models which assumed things like zero technological growth. It assumed things like arbitrary values for quantities of pollution and so forth. Now, it might be a little hard to parse out what's going on here, but what I can point out is the curve that goes from the top left to the bottom right is resources. So the assumption is no technological growth and a complete running down of resources in proportion to the growth of the population, which is that darkest curve in the middle there, the solid black curve. Now, the Club of Rome in 1991 said this: "In searching for a new enemy to unite us, we came up with the idea that pollution, the threat of global warming, water shortages, famine, and the like would fit the bill, but in designating them as the enemy, we fall into the trap of mistaking symptoms for causes. All these dangers are caused by human intervention. and it is only through changed attitudes and behavior that they can be overcome. The real enemy, then, is humanity itself. Now, this became United States policy. Put the next two slides up. So in 1960, the future Secretary of Defense and then Secretary of Energy, James Schlesinger, said this: "Economics is the science of choice in a world of limited resources. We have gone around the world spreading the gospel of plenty, raising the level of expectations. But in the nature of things, these rising expectations can never be satisfied. We must, in our strategic policy, return to the days before the Industrial Revolution and prepare to fight limited wars." And then, in 1974, authored by Henry Kissinger, "The U.S. economy will require large and increasing amounts of minerals from abroad, especially from less developed countries. That fact gives the U.S. enhanced interest in the political, economic, and social stability of the supplying countries. Wherever a lessening of population pressures through reduced birth rates can increase the prospects for such stability, population policy becomes relevant to resource supplies and to the economic interests of the United States." Now, that is geopolitics, that is empire, and it's one and the same as the environmentalist movement. This is the basis of it. It's the basis of thinking of poor, abused children, such as Greta Thunberg, and it's the thinking of very witting players, such as banker Mark Carney. Now, this is a Zeusian outlook. This is a Zeusian policy, and the intention is a colonial policy. It's based on a lie about the nature of man and a lie about humanity's relationship to nature. Now, that is the basis of the inhuman side of the argument that there are limits to growth, there are limits to resources. Now I want to shift over to the human side. So first, to introduce that, we're going to see a clip of Lyndon LaRouche.
Mankind does not live naturally. Mankind's achievement is to be highly unnatural. I don't want to encourage certain tendencies by that, but that it is unnatural in the sense of the typical ordinary physical chemist who is not a physical, is not really a competent physical chemist. What is the physical chemistry of the universe? We have the physical chemistry we identify with the non-living, that is, which has no antecedent as an organized process. Then we have processes which are living processes inherently, or residues of living processes. Then we have humanity, which is not the same, quite the same thing as any other form of living process. So we have the three categories. These are dynamic, they are universal and dynamic. They interact. The universe is a composite of these interaction of these three phase spaces and everything that's derived from it. So now, how do we live? Let's take a typical case of iron. How do we get iron? Well, we could get iron in many ways, hypothetically. But how do we actually get it? How have we gotten it in terms of the 18th and 19th and 20th century? We went to areas where a lot of little animals and plants died. We went and they robbed their graves for iron. Now, iron is all over the planet. It's a universal thing. But why do we go and rob graves to get iron? As around the Great Lakes area, it's one of the great deposits of iron. And we rob the graves of the little creatures that died there. That's how we get iron. Why? Because the little creatures who used iron as part of their biological process, would, when they died, they would have left a concentration of iron in their little dead bodies. And you can go there and say a prayer over them. So therefore we found that the sources of richest concentration of iron ores for us, such as bog iron in a New Jersey swamp, which is where the Revolutionary War got its metal, iron from New Jersey, from the bog iron swamp. So we concentrate on the grave robbing of living processes. And we find that we go and we take the areas which have the richest concentration of iron, which means the least heat, the least coal used up in order to refine the stuff, and we leave behind the things that are not quite as efficient, that consume too much power in order to reduce this thing to a form of usable iron. Now we find out that by doing that, we tend to exhaust the richest resources of various kinds, left behind in the graveyards of various kinds of species. That's how we get them. We have the lithosphere, and on top of this you have a biosphere, which is developing. It selects certain materials from the environment, grabs it, takes it into their bodies, food for this little creature. These things die, and they leave behind these deposits. And you go running around the world to find out what the kind of species was loose in this area, and they will give you the best concentration of this kind of deposit from the periodic table. But then you're using it up. Are you using it up? No, you haven't diminished the total iron in the universe. On the earth, it's still there, it's still much, but it's now dispersed. It's not in graves you can rob anymore. You have to go out and rob other graves, or you have to take other resources, and you have to get more powerful means of reducing resources in order to make them equivalent to what had been the richest resources of this iron. So the essence of the thing is, for humanity to exist, several things are necessary. Humanity must increase its power, measured in heat energy or heat power per square kilometer, per square centimeter, or smaller. And by increasing our power, by increasing the energy flux density of the power applied, we are able to make poor resources better than what had been previously considered rich resources. To do that, we have to develop infrastructure, a total systemic infrastructure. We have to develop an infrastructure which is able to organize the application of energy, power, in various ways, which makes it possible at various points in the earth to extract economically a raw material from the periodic table, and to distribute it, because you're getting it here, you want it over here. That requires a system of power to deliver this damn stuff. So therefore you can take the increase of the energy flux density per capita and per square kilometer of the planet is a limiting consideration. So now let's look at economics from that standpoint, which is called the science of physical economy, which in its modern form is based on the work of many scientists, especially the followers of Bernhard Riemann, such as Max Planck, such as Albert Einstein, and Vernadsky. That is real economic science.
Okay. So with that in mind, I want to come back to the idea of fire, of humanity's changing relationship to nature, as you just heard expressed by LaRouche. Now, I think sometimes we have sort of a funny idea of resources and what makes something a resource, or how resources come to be part of human society, almost like, a rock somebody tripped over, or some greedy oil magnate discovered oil and is selling it off and making tons of money, or that it's driven by the fight for survival, right? Like, oh my gosh, we just burned up all the coal. What are we gonna burn now? Oh, oil. Let's burn up all the oil, right? But I think we don't really have a sense of what designates a resource like iron as a resource. So I want to come back to the image of Prometheus and the different forms of fire. And the idea that I want to get at is that when we talk about resources, when we talk about raw materials, it's not about the stuff. It's not about the material per se. There's nothing self-evident in matter as such, as a resource. And the reason is that matter changes in relation to our changing mastery of principles of the universe. So I hope to illustrate some of that with a few examples. So the first example is copper. And here you see some copper. The use of copper for humanity goes back thousands of years. In the late Stone Age, which is, let's say, maybe 5,000, 5,500 years ago, human beings used copper like this, native copper that we found in the earth. And this native copper was pliable. It could be hammered into different shapes, and it would keep an edge much better than stone. Okay, so here, that's copper. Let's go to the next slide. Here's some copper. And you might say, what? That looks nothing like the shiny metal that I saw a moment ago. This is copper, sort of. This is a mineral called malachite. And sometime after 3200 BC, which was more than 5,000 years ago, human beings developed the ability to turn rocks like malachite into metal, meaning that somehow human beings developed the technology of underground ovens, kilns, which could produce temperatures over 1,000 degrees Celsius, where they would use layers of burning charcoal layered with rocks like malachite, which would melt the metal contained in the rock. The charcoal would remove the oxygen from the mineral as it melted, leaving pure copper behind. Now, this is incredible. And it was discovered a little bit later that by mixing copper with tin, which for a couple thousand years was widely available in many parts of the world, that we could get bronze. So we're now mixing metals together, metallurgy, and creating a new substance that's stronger than copper, that has a lower melting temperature, that can hold an edge better. So you think about what's going on here. You have a kind of fire, modulated fire, which doesn't occur naturally, which can produce temperatures upwards of 1,000 degrees, hot enough to melt rock. And out of it, human beings are creating new substances through transformation of materials to induce in these substances more suitable physical properties: sharpness, durability, lower or higher melting temperatures. Now, following this with the Iron Age, we know, based on certain properties of iron, and you just heard LaRouche talk about iron, we know that humanity had the capability of producing temperatures in these kilns of over 1,500 degrees Celsius, 50% higher. Now, copper, again, moving forward many, many centuries into the 18th and early 19th century, copper, again, plays an important role in the discovery of electricity and the electric current. We had the work of Luigi Galvani and then his successor, Alessandro Volta, who used copper to create the first battery, the voltaic pile. So here you see the voltaic pile, where you have a stack of discs of copper and zinc. And between these discs of copper and zinc, you would have a cloth that was soaked in a salt water. And what this induced was a process of the flow of electrons from one end of the battery to the other. And you see the two terminals of the battery there. So here, copper is playing a very important role again, but not because of its hardness, not because of its durability, its ability to hold a sharp edge, none of these physical properties. Copper is chosen and it's valuable because of its ability to interact chemically with the salt water to allow a flow of electrons. Now, with the later continuing work of people like Ampere and others on electromagnetism, also the electric motor and the role that that came to play in industry, copper's ability to conduct electricity, copper's strength, its flexibility, its lightweight when pulled into thin wires made it incredibly valuable. So now I want to jump ahead just a little more and look at the development of modern chemistry. So we're going to look or mention the contributions of Dmitri Mendeleev. So you have kind of this wild-looking guy there. Mendeleev stood on the shoulders of Antoine Lavoisier, and he created modern chemistry, the two of them. Mendeleev created the periodic table of elements. Now, I want to pull up this next slide. Okay, so here you see two rocks. Now, the rock on the right and the rock on the left are quite different. If we look at the rock on the left, it's clear, it's extremely hard, it's a poor conductor of both electricity and heat. The rock on the right is black, it's opaque, it's soft, and it's a very good conductor of electricity and heat. Now, go to the next slide. Here we see the chemical formula of the rock on the right. And here we see the chemical formula of the rock on the left. They're both pure carbon. You have graphite on the right and diamond on the left. Now, both of these are the exact same element, pure carbon. So what properties do we say carbon has? Is it soft? Is it hard? Is it a conductor? Now, Mendeleev said you cannot approach this by looking at what things are. You have to look at it in terms of what things do. What actions do they take, or can they be induced to take? What transformations can they undergo? What compounds do they enter into? And by taking this approach, Mendeleev was able to figure out the properties not of graphite or diamond or carbon dioxide, carbon monoxide, glucose, any of these carbon compounds, but he was able to figure out the characteristics of carbon. For example, he asked questions like, does it enter into compounds with other elements in pairs, as hydrogen does when it forms a compound with oxygen and makes water? Does it tend to form strong acids, strong bases? Does it join with metals easily to create salts? And by asking these questions, he was able to find affinities in the behaviors of certain elements that never could have been seen by asking what things look like. He found, for example, that fluorine, chlorine, bromine, and iodine, the group that we call halogens today, that these all shared similar characteristics in their actions. And it was through this kind of process where Mendeleev was looking for the invisible characters of the elements, the unity of matter, that he was able to find an ordering process, an order of these elements, and produce the first periodic tables. So here you see one of his periodic tables. I don't know which writing this is from, 1860 something. And what you see here, what I want you to notice is how similar, I mean, it's the beginning of what we call the modern periodic table. But the other thing I want you to notice are the gaps. There are gaps where he knew an element should go there, but no known element existed. So we'll come back to this. Now, shortly after Mendeleev was doing his work on the elemental nature of matter and its action, which formed the basis for modern chemistry, shortly after that, humanity started to develop a different idea that the periodic table of elements as such wasn't fixed. It was fluid, meaning that there was something more elemental than the elements. So let me give you an example to show you what I mean. So this came with the work of people like Röntgen, who discovered X-rays, Becquerel, who discovered that uranium gave off some kind of radiation, Marie and Pierre Curie, Lisa Meitner, and others, who showed that elements such as uranium and radium radiate, that they give off tiny particles of mass. Now, if you thought that the atom, an atom of a certain element, was the most elementary part of nature, and suddenly this elementary part is shooting off a small particle, this is going to completely blow your sense of the ordering of nature apart. Now, what was discovered is that over time, through this process of radiation, of giving off radiation, elements will actually change positions on the periodic table, transmuting from one kind of element into another. People like the Curies worked primarily with radium and found that as it gives off radiation, it decays into a new element, which they called radon, which had never been discovered before and filled one of these gaps in Mendeleev's periodic table. Now, this early work on the nucleus, the atomic nucleus, led into work a little bit later of the artificial transformation of elements one into another by bombarding them with these small particles like neutrons. There was a woman in Germany named Lisa Meitner, and Lisa Meitner, working with a team, worked with uranium, and they found that when they bombarded uranium, instead of hopping down a position or two in the periodic table, or maybe jumping up a position or two in the periodic table to become one of its neighbors, uranium actually decayed into elements which were roughly half the size. Now, this turned out to be a process which was believed to be completely impossible, which was nuclear fission. So here you see at the top a neutron, which is being shot at an atom of uranium-235. And that uranium is excited and fissions into two smaller elements, krypton and barium, and 3 neutrons. Now, it's sort of funny to see that as a cartoon, which is what we're used to in our textbooks. But this was really an incredible, incredible discovery. Now, there's something else incredible about fission. Actually, can we put that back up? When we split uranium into krypton and barium and 3 neutrons, if we take the masses of those products, those 5 little pieces of product, if we put them back together, they add up to a mass which is less than the original uranium. So let me say that again. The original uranium, which fissioned, uranium-236, fissions into parts. It breaks into parts. And if we put those puzzle pieces back together, the thing that we put back together is less, has a mass which is less than where we started. Now that is called the mass defect. That missing mass, as we know from Einstein's famous E equals mc squared, that missing mass was converted into energy. And that is the basis of the incredible power of fission energy. So after fission was discovered, it was realized that if you could get two lighter elements, like hydrogen and helium, to join together into a heavier atom, that the mass, what was called the mass excess, the fact that the pieces would weigh more than the final product, that mass excess would release even more energy than the fission process. And this is fusion. This is really the frontier, the spear point of research and breakthrough for humanity's fire, new forms of fire. And let's put up the next slide. So I want to look at this. I think I may have shown this before in the first class. I can't remember. So this chart, as you see at the top, is a chart of energy density. And it's expressed in terms of how much fuel it would take to meet New York City's electricity requirements for 1 year. So I want you to look for a moment at the column of fuel source. So you see from top to bottom, our fuel sources go from wood to coal to petroleum to uranium, deuterium, tritium, and then finally matter, antimatter. Now, the first three fuels, wood, coal, and petroleum, are chemical fuels. These are mankind's earliest fuels, wood and coal, and then eventually petroleum. Once we get into uranium, which is fission fuel, and then deuterium and tritium, which is a fusion fuel, we're in a completely new domain. So I want you to think of this process of transformation from our use of resources, the earlier resources to the later resources, as developing new types of fire. And what you see on the right, under the column labeled tons, is how many tons of that fuel source it would take to meet New York City's electricity requirements for a year. And you see with wood, 16 million, with coal, 8 million, with petroleum, 5 million. But then, with fission, with the nucleus, 55 tons. With fusion, less than 1 ton. And then with matter, antimatter, which is really just in the very beginnings of hypothesis, you see the relationship there. So what we're looking at with resources is we're looking at the process of discovery of mankind's relationship to nature, and we're looking at the increasing power that gives us to change nature, to support humankind. This is human. Every time we've revolutionized our understanding of what makes the universe tick, of how it works, of what's running it, we create a new resource base. We create resources that were invisible to the prior state of humanity. That's the secret. That's the kicker. And if, like Zeus, like Malthus, like Julian Huxley or Obama, you think that human beings are just animals, then you think that resources are limited and we have to stop development. And you notice that none of these people volunteered to go first. But if you think that human beings are what I've said and what LaRouche insists, then you realize that each discovery opens up a completely new platform for power and development that could not have been counted before because it was invisible, it didn't exist. So unless you think there's a limit to the human capacity to discover, and I challenge you on that, unless you think there's a limit to the human capacity to make new discoveries, which were unthought of by past societies, including us, in reference to the future, then you have to give up the idea that there's a limit to growth and that there's a limit to development. So I want to end with this thought, and that is that when we finally develop control over fusion power, and even before we have commercial fusion reactors, we will be able to build fusion rockets. The reason this is so important is because with fusion fueling our rockets, rather than chemical fuels like we have today, we will be able to reach Mars, Jupiter, Saturn, the outer reaches of the solar system in a time that makes it possible for exploration, to set up science stations on the outer reaches of the solar system. That's completely unthinkable and impossible with chemical fuels today. Now, we human beings have been stuck on this lovely but small planet for our entire existence. Our planet is one of 8 or 9 if you're a Pluto partisan, but our planet is one of just a handful in a solar system, which is in a galaxy with 250 billion other stars, which is in a universe with at least 2 trillion galaxies, at least. So that is a resource base. So I think that's where I want to leave it. I'd like to open it up for discussion on anything in this class or in the previous class. And including in the mix in the discussion, we should get some reports on the homework if people took a stab at that.